Well, welcome everyone. Thanks for making it, the commute and everything. So I really appreciate all of you being here. So today's topic is right there. We're going to show you what automated machine learning looks like, and it's focused more on folks like yourself. If you're a BI analyst or playing with machine learning, or even want to learn a little bit about machine learning, I plan to go through a little bit of what a supervised learning is, just some basics around machine learning and then we'll do a little demo on how to do automated machine learning by pushing a bunch of buttons, and you can build some awesome models. So, I want to give a 30-second intro to supervised learning. So what is supervised learning? So basically, you have a bunch of data, right? So this is a data set from UCI Machine Learning Repository, which you can find it. It's called Portuguese Bank Marketing Data. So it talks about, it's got data on marketing campaigns, and then at the very end, you have a column. This is from historical data. And you see a yes or no column here. This actually tells you whether a customer, after being targeted by marketing campaigns, whether they signed up for a term deposit or not. So what's a term deposit? It's like a CD, like a fixed time, the fixed interest rate. So there is motivation for a customer to go and open CD accounts in any economy. And so the thing is, if you actually look at the data, it's got data like, age of the customer, obviously it's anonymized, there's no names here. What kind of job the customer holds, marital status, education, and then whether that customer has a credit in default, what's the yearly, average yearly balance, whether they have a housing loan and a personal loan. So this is what we call as a profile data, mostly, right? And the thing about building a data model is that you can have both profile data as well as behavioral data, right? And you can also have exogenous data coming from outside the bank, for in this case. So you can see that there is some campaign-related variables here, and also some exogenous variables that is not shown here are things like, like an index, employment index, or a consumer price index. So you can put all of this data, and what we're trying to do is to learn from this data on what kind of variables actually result in a customer opening a deposit or not. So the goal of the supervised machine learning is to actually supply this data to an algorithm, and the algorithm is going to find out the combinations or the unique things about these variables that can actually help you predict the outcome. And as you know, this is called supervised learning because this outcome is already labeled, right? So H2O as an open source product has both supervised and supervised learning, but for this meetup today, for this talk today, we're only going to be focused on supervised learning. Okay, so with that, so this is exactly what we're trying to do, right? So we want to find a model using all these variables to predict Y, and we want to learn that from historical data, and we want to use that model in the future. When you get this kind of data, you can actually use the model to make a good guess, saying that whether the customer is going to open or not, and that's predictive analytics for you. Now, what are the challenges, in this data? So if you actually look at it, if there are like 100 rows or 200 rows, you can kind of eyeball them and kind of like come up with some rules. You can derive some rules. That's what a lot of people do outside machine learning. They look at this and say, oh, if the balance is more than this, seems like the customer is opening a term deposit. Or, if a customer representative talked to the customer for more than X number of seconds, sounds like, so you can come up with these initial rules, but it's not going to get accurate. You're probably going to be like 60% accurate. And this is why we want to leave the problem to the machine. The challenge today is that, okay, so before that, let me talk about how data scientists would take this problem and build a model today, okay? So the first thing they would do is to actually identify all the variables, also known as features, or you saw the columns, and then find the Y, and then determine what the Y is. The Y could be a number, it could be a yes or no, or it could belong to multiple classes. And the first thing they do is to formulate the problem. What are we trying to predict? The second one is they go about transforming all these features into, for example, they would convert numeric values to categorical values. And then sometimes categorical to numeric, also known as encoding, and then do additional transformations like convolutional neural networks and things like that. Then they would actually separate the data into training and test sets. So for example, 75% training and 25% test set. And then try a few algorithms like GLM, random forest, this big word soup here, right? So there's like a lot more than this. They would try all these different algorithms, build a model on the training set, try to predict the test set, and if the accuracy is really good, then you got yourself a nice predictive model. Okay, so that's like the hello world of supervised classification. And then at the very end, they would actually hand off this model, and then you can either do batch scoring for all your customers, like if you have like 100 million customers, like for example, eBay or PayPal, you can actually run them and score them in batch every day, rank order the list of customers who are most likely to do something, and then hand it off to marketing or for follow-up. So that's called batch scoring. Sometimes you want to do real-time prediction, like health data. If you want to train on health data and you want to see if somebody's going to have an illness or a hospital readmission, you can also do real-time scoring. So that's exactly how this model is going to be used. And the last part is the tricky one. So, while you're doing all of this, you still have to explain to business exactly what the model found, right? That's the hardest part. So the more complex the algorithm you use, like deep learning and more advanced algorithms, this is going to get harder and harder. So this is a big, big challenge. And then the last one is while you're building these models, if it takes you like 4 to 6 weeks to build a model, data has already changed. And the parameters have changed, the exogenous data has changed, the temperature has changed, the weather has changed. So many other things can happen. So the key is to build models really, really quickly. That's a really big challenge. So, as I said a little bit before, so what are the common challenges with supervised learning, right? This is something, the first slide that I showed you, this earlier slide I showed you is what a junior data scientist would do. Whereas if you're a senior data scientist or somebody in your team, or you're trying to become a senior data scientist, then the challenge would be how to find the winning features. What combinations or transformations of features should I do in order to boost the accuracy? Why accuracy is important? Because if you don't have good accuracy, you're going to get a lot of false positives, which means that your operations team is going to be wasting a lot of time reaching out to customers who's never going to open a deposit, and you're going to be wasting a lot of dollars. And the other big challenge in supervised learning is class imbalance. For example, if you take an example like fraud, you're going to have less than 1% of the data, or even like less than 0.01% of data are fraudsters, whereas 99.99 customers are not fraudsters. All the data is benign. So how do you build a model? So when you use a naive way of building models, you're going to get like, it's impossible to achieve high accuracy with standard methods. So you can go to a Coursera course, or you can go to a Udemy course. You can learn about the basic algorithms. You can build a model. Your model will work really fine if your data is 50-50, like 50% of fraudsters and 50% are benign, or 50% open term deposit and 50% did not. But in reality, the data is always skewed, which means that the algorithms have to work much harder, and you have to come up with really advanced techniques. And that falls in the realm of a super data scientist in your team, and they are hard to find, right? So again, when you build a model on training set and you try to score on the training set, you're going to get 90% accuracy. The problem is when you build a model on training set, and when you actually score on a set that's not part of the training set, your accuracy will drop quite a bit. Or if you do a really good job of training and predicting on the same set, it's called overfitting, which you don't want to do that. So, and there are a lot of techniques against to avoid overfitting, and that goes into the realm of advanced data science. So here's a standard challenge. Some of you might have run into it or heard about it. Getting to 75% accuracy on the first try, quite possible. Sometimes you can get luck out with that. If you use a deep learning algorithm, maybe you can get, but going from 80 to 85 on something like a class imbalance data will usually take weeks, because you got to go and do all the feature engineering again. And getting from 80 to 90%, all without overfitting, is going to take months. So a typical model, that's a production level model, would typically take weeks to months to build, and that's an ongoing challenge. The thing is, there are so many algorithms out there, and every algorithm has a lot of parameters, right? So if you take I'm just going to come up with an algorithm like random forest. So it's got a lot of parameters. You can use the default values, like number of trees, number of splits, there's like bias, there's like all kinds of things you can add to an algorithm, and there are like a million combinations of parameters that you can come up with in order for the algorithm to perform better. The problem is you can't try all of them on time. It'll take a lot of time to tune the algorithm in order to get you the best model possible. So not only you're going to experiment with multiple algorithms, in reality you're going to be tuning all of them, and it's going to take a lot of time. The second one is speed, right? So how do you reduce the model building from days, weeks, and months to hours? That's another challenge. As you know, GPUs are there. Deep learning uses GPUs. GPUs accelerate algorithm performance quite a bit. So that's another solution, but speed is extremely important because you don't want to lag behind, for example, the flu season, right? So you don't want to take 6 months to do it, right, when the flu, or the bacteria or whatever, the virus has changed its form. So you want to be able to constantly build models really quickly and also be accurate. So, and then how do you go to production? Let's say you build a really complex model, use 4 algorithms, do all the parameters, like how do you package it and give it to DevOps so that you have this continuous integration type of model by which you're constantly updating the models in production. So that's another big challenge. And the more easy we make it, the grease the wheels, the faster we can go to production, even if it's a complex model. The last one is probably the most challenging one. When you actually use a complex algorithm, sometimes you can get 85 to 95% accuracy without overfitting using things like deep learning. Then the problem is, how are you going to explain to the business what the model is doing? Now, this is a trade-off between accuracy and explainability today, and there are a lot of new technologies that's coming out called explainable AI, by which you can not only get good accuracy, but you can also explain to a business in very simple terms with respect to the original variables and say, these are the reasons why the model is doing what it's doing, like marking somebody fraudulent or denying a loan or that sort of thing. So today, the adoption of AI is very poor. With standard machine learning tools that you see open source sometimes, is that off the shelf also, is that you're able to get really high accuracy, but you can't go to a regulator or, or a compliance department and explain why your model is doing what it's doing. So these are all the challenges that are general challenges, well-accepted challenges. So I want to actually show you a product from H2O called Driverless AI that solves a lot of these problems and makes it easy for anyone to actually build a high accurate model. You can actually do it on your laptop. You can spin up Driverless AI on Amazon EC2 or Google Cloud or Azure. We are in the marketplace for all the 3 cloud vendors. And if you have an NVIDIA DGA1 GPU box, we will run on it. So this Driverless AI demo addresses all the problems and challenges that I just described today. So let me spin up my instance here. Let's see. Meantime, if you have any questions, let me know and take a couple of seconds for me to bring up this. Okay, maybe you should turn off this light. This one. Yeah, so Driverless AI is a self-contained, it's an extremely easy to use product. Which means you can bring in any data set as long as it's got rows and columns. We don't support images right now or audio right now, but we do support text and time series. So when I actually used the Driverless AI the first time, I actually went to a Kaggle website or the UCI machine learning repository. There's a lot of data sets. You can look for classification or regression data sets. You can throw the data here, right? So we have connectors to I'm only showing a few connectors, like you can upload a file like a CSV file or Excel spreadsheet, similar to what I showed before. Or you can, we have connectors to HDFS. So if you have a Hadoop file system where all this data is stored, you can pull the data from there. The last one is, if you have an S3 bucket holding the data, you can actually provide an S3 URL to get the data because it's running on the cloud, so you can go and get from either Google file system or you can Azure storage or an Amazon S3. So we have connectors to all of that. And as you can see here, we will not be writing a single line of code, but the model that is going to come out of will be world-class model. Like you can't beat it. The reason for that is at H2O we have the top 7 Kaggle grandmasters working here who actually built this product. So they have come up with like really awesome recipes on how to take the data in the natural form, transform it, do feature engineering, and also run multiple algorithms on GPUs, and then at the very end you're going to get a model. And not only that, you'll be able to explain what that model has. And whatever takes like weeks or months sometimes can finish in hours or in a day. So this is the same data set that I showed in the first slide. Just to walk you through, there is an age. Here's the age column, so you can see a distribution of that. What kind of job, right? So these are just descriptive statistics, nothing fancy here. The interesting thing here is that driverless AI would automatically find out the data types and actually map it, and then it'll automatically determine what is categorical, what is numeric, if there is a date inside. In my past, I've spent probably 80% of my time trying to get this right. So, and you can have like missing data, outliers, but driverless AI would actually work with that, right? Let me actually show you the data here as well. So you can see, I don't know if you can see here. Yeah, so this is a job, marital status, right? The same sort of like a big matrix of things. On the rightmost corner, you'll see whether a loan, whether a term deposit was open or not. So all the data is here, and you can actually do this in a laptop really quickly. There's documentation on how to download driverless AI. This is like a 21-day trial, but you can actually download it, bring in your data, and you can show to your data scientist. If you're a data scientist, you'll be amazed by how it has figured out what's the right algorithms, what's the right parameters, and then also be able to explain what's happening in the data. Now, the context of the whole meetup is about BI. So where BI comes here, right? So if you're a BI analyst and you've been playing with KPI or MicroStrategy or Tableau and you've been looking at all this data, even like Excel charts and things like that, sometimes it's easy to spot certain trends that can actually lead to your outcome. But at some point in time, you want to actually hand it off to something like this, like an AI sort of thing that actually goes and figures out all the connections between the variables and the outcome, and also be able to explain to you what exactly is happening in the data. So this is kind of like we do the AI first, and then we kind of do a little bit of BI later. So if you're already doing BI, you can actually compare your results and actually take advantage of this AI technique. And so as a BI analyst, you're going to be a lot more smarter in explaining to your business. And not only that, you actually build an AI model yourself, right? And the requirement is there's no Python. If you know Python, we have a Python API for all of this. If not, you can start with a spreadsheet or a CSV file, build a model, explain the model, and then and then actually even give it to production. If you have, you can talk to DevOps. And of course, you can always consult a data scientist, because part of this tool also shows you some data science metrics like accuracy or false positives and negatives, and you can certainly have a data scientist in your team work together and build an awesome model. Okay. So then I want to show you like a couple of features here. This is a descriptive statistics, shows you a bunch of histograms on the data. You can see like consumer price index varies from 92 to 94. There is a Euribor 3-month index. This is sort of like an interbank interest borrowing rate, exogenous data, right? While you're doing all this, you may have all the data about your consumers, but you should also look at socioeconomic metrics. You're welcome to bring it in. You can also bring the weather if you want, and you can bring in any kind of data inside without thinking about how is it going to affect my model. The whole goal of AI is no matter what data you bring in, it is going to figure out the connections. If something occurs commonly across all customers, it's going to ignore it. It's only going to find the things that are useful, and it's going to completely wash out the things that are not useful. So you don't have to like prejudge your model saying that, should I bring this feature or not? Is this going to be important or not? I say leave it to the AI. Okay, so you bring in as many as you want. Sometimes some people like to call it kitchen sink. Just throw everything at it. Let AI figure out what the connections are, and then you can work backwards, go back and add in more features or remove features that you don't like. So you can actually work in collaboration with the AI tool in order for the AI to teach you about your data, and then you're telling AI, why don't you try this? Why don't you try that? I think that's kind of the model that you'll be seeing here. So, we have a product called we have a feature called AutoViz. This is generally like a BI, but it's a very intelligent type of BI. If you have like 200 columns and you want to know what's going on, if I show you like 200 histograms, you're not going to get any insight. So what would be interesting is to only show the visuals that are interesting, right? Out of the 200 columns, are there any columns that are a little bit, kind of skewed to the one side or doesn't follow a beautiful bell distribution? So if I click on the skewed histograms, you can see this like a carousel here. And we only show you the histograms that are, skewed towards one side or have gaps and, doesn't look straightforward, right? We also show you outliers in this case. So there's an outlier here, right, where there is highly populated. There are more counts here, whereas there's one standing out. You can actually click on it and see what the outlier is. This is a very simple feature. Again, for the driverless AI, there's nothing actionable here. You don't have to go and delete it. So the product actually takes care of, outliers, missing data, data that's not formatted well. Let's say you have a lot of dates and there is one date that doesn't fit the format. It'll take care of all of that. And that's the whole goal of AI, is that it reduces the amount of manual effort for you in order to get a really good model, okay? So let's do the machine learning right now. So the only thing you have to do is to go and click the predict button. I hope the screen is visible. The font. So the next thing you would do is, it's actually telling you there's 41,000 rows and 21 columns. The next thing you would do is to actually go and pick the target variable or the target column, what you are trying to predict. We want to build a model to predict that. So the AI automatically, by looking at these columns and distributions, comes up with some sort of an explain plan. If you're from the SQL world, I'm sure you're aware of an explain plan. It tells you a strategy on how to solve this problem, right? So as a data scientist, you can look at it and say, oh, well, I think I know what it's doing. But if you're not, we are already providing you some defaults and some knobs here. So the only thing you need to do is to tweak these knobs, and I'll show you how. So the first knob is called the accuracy setting. Obviously, everybody wants accuracy of 10, but the trade-off is it's going to take a long time. It's going to take a lot more time to build a really good model. Sometimes you want to try a low accurate model. In the driverless AI world, low accuracy will be like 80% or 75% automatically. So I'm just saying, but if you want like 95% accuracy or 90% accuracy, you want the AI to work harder for you in order to get to the answer. So you can actually tweak these knobs. The second one is like how long, how many iterations you want to do. You can, the more time you give it, the more things it will try in order to build a good model. And the last one is called feature engineering knob. So again, 1 to 10. So what this means is we are starting with 21 features or columns. The driverless AI would actually go and build thousands of columns from those base columns by combining columns together, by binning, by doing all the transformation a data scientist would do, and come up with a huge feature list to see if there is something significant there. Sometimes adding 2 columns has got more predictive power than using it alone, and we're actually going to try some of those. So basically that's it. So we can go with the defaults, and the last one is a scorer. So there are multiple scorers. This is a classification problem because we're saying yes or no. But if you're trying to forecast a number, it would be a regression. So for classification, these are the most popular scorers like area under the curve, Gini, and so on and so forth. So you can actually get help on all of them. Not all scorers are good for all problems, but we automatically choose the one looking at the data. So this is another step that's automated for you. And then the next thing you would do, I'm going to set the accuracy to really low, and then because we want to finish it on time. And then I would make it a little bit a simpler model, and then we say launch experiment. So here, the next thing that's happening here is that the driverless AI product would actually go and look at all the different columns. It started tuning the models. And the algorithms that are running here, all of them are rewritten to use GPUs. Okay, so if you run it on Intel CPUs, it's going to be like 10 times or 25 times slower. And you can see that it already built 4 or 5 models, and starting with an accuracy of 0.86 already. Some of these algorithms are, and you can also see the variables that are important in the data automatically in the last model. So this is a curve called receiver operating characteristic, also called a ROC curve. And basically you have false positives and false negatives on both the axes. but really we are actually pointing you to the areas where the accuracy is really higher. So again, you don't have to know whole lot here, but you can certainly go back, work backwards, and probably go to Wikipedia and understand why. Then we are actually doing what is tuning those models, like tuning those algorithms, the hyperparameter tuning. Now, when we take the big feature set, we start with a sample. We call it a gene. We start with a gene, and then we evolve using sort of like a genetic algorithm. So we start with a bucket of features, and then we build a model, and we see that, and then we build another one, and we see that some features have more value than the others. We drop the old ones, and we pick up new features from the pool, and we constantly evolve that. So here the accuracy is really low, so it finished already. You can see it took 3 iterations, probably built like 20, 30 models. In reality, it'll be like thousands of models will be built, and all these features will be, we're doing feature evolution at the same time. Parallel, we're also doing model tuning, and they all talk to each other. So basically, we're trying to find the signal, right, over evolution. So all of this happens under the covers. So the reason why for this talk is that you can see that I didn't write a single line of code. I brought in the data, and all I'm doing is setting these knobs and picking up the scorer. And here we are building up, build a model that's beyond what a normal data scientist can do, right? If you think about even a senior most data scientist, it takes them, you got to go through the iterations, the model tuning, even finding the right features in order to get a really good lift is going to take a lot of time. Here we are automating the process of machine learning, and that's why it's called auto ML.
Yeah, that's a great part of ML, but what's the magnitude? Like, are you talking about like maybe a million, $500,000 experiment to get the result?
Again, we actually look for convergence as well. So if the features are not improving, we do early stopping. But these settings are all not linear settings; they are log settings. So again, we will build, like I said, maybe like 10,000, 20,000 models in the worst case scenario. Thousands of features. We're not talking about millions of models. And the reason why we're able to do that is because of our knowledge, domain knowledge from our Kaggle grandmasters, who actually contributed code to this product, by which we do very smart decisions based on both domain knowledge as well as the recipes that they brought in, is allowing you to choose the features and evolve the features in a very scientific way to some extent. So initially there's going to be some random stuff, just like life. From the very cell, different chemicals are there, and then life evolves, and then it evolves over time. And sometimes it takes longer time to find a better model, but we'll be searching, we'll be finding new features. So it's kind of like a genetic algorithm, right? So it's not going to be like a crapshoot type thing, wherein you're trying everything, because you cannot try everything. So it has to be done in a very intelligent way, and that is part of the product. Heyman?
So to answer the question of to give you a magnitude, that it is a function of the size of the data and the setting that you provide in accuracy and time. To give you a rough estimate, the number of models that would be tried typically would be in the range of hundreds to thousands. Yeah, not a million. Yeah, not a million or so, but roughly in the order of hundreds to thousands. And the system has intelligence built into it to detect convergence, which means that if for a continuous of 5 iterations, or the number of iterations is also dependent on accuracy. The more the accuracy, the number of iterations we try is higher. So let's say for accuracy of 5 or 6, the iterations that we try to detect if we are getting a better score is 5. If you bump it up to 8, we will try for 10 iterations. So if we are unable to get a better score within that iteration threshold, we scientifically determine that probably we have got the best signal out of the data and we cannot proceed, and that's where we early stop.
So you basically abandon earlier, right?
Sorry?
So you abandon some of the model, maybe after first five iterations, you see that.
Right, we always, in each iteration we try to select which is the better performing model, and then the ones that are better performing, some of them proceed ahead, new models are created, and then they fight with each other.
Okay. So the next thing is, okay, we build a model. What next?
So I had a quick question. So in addition to trying out different models or algorithms, and then that's on the one dimension, the other dimension is the feature discussion we just had about which features to use, derived or the original feature set. There's a third dimension to the problem as well, right? Which is that you're breaking the data set between a training data set and a test data set. And that is also being manipulated now because obviously you want to make sure that you don't get into a situation where you've got a fantastic number with your training data set because perhaps you've overfitted. And once you've done that, once you actually apply it to the test data set, the numbers look pretty bad. So, so you're essentially, if you're sort of thinking of tweaking a set of knobs, you've got three knobs. You've got, that's what the machine is doing. You've got the model knob on the one hand, you've got the number of experiments, the number of features that you're using on the other hand, and then the split between the training and test data set, which is also being manipulated so appropriately to get you the right predictions, correct?
Exactly. So any of the results here are post-cross validation. So every time, that's exactly how we tune the model, right? So we do cross-validation internally before the model says that, then we go and try the next one. So along the way, cross-validation is also done in some way. So we don't do the final cross-validation. We do the final cross-validation some other way, but that is also encompassed in the product. Again, that's a very manual task, an arduous task. To find a model, do the cross-validation, look at the metrics, right? Try another one. So that is also part of the automation. That's a great question. And Hemant, yes?
Yeah, out here it is controlled by the accuracy knob itself. The higher the accuracy, the more stringent the cross-validation strategy goes. So let's say if the accuracy is less than or equal to 7, then we do a 1/3 split, and per model we have a cross-validation happening. But if you increase the accuracy to 8 or above, then there is 5-fold cross-validation that comes in. But it's also a function of the data set size too. So there is an intelligence built into it on how to start it. But you are right, yeah. So we just reduced one knob and combined that into accuracy.
Yeah, we want to make it really easy for folks to try this out, play with it, and then you can, and then that kind of, you can do more advanced stuff, obviously, on top. But these are the chores that most data scientists spend a lot of time on, right? So as a business analyst, we're used to like BI world coming from analysts and getting into data science. You can, I used to be that long time ago, and when I started playing with automated machine learning inside H2O and outside H2O, I found that, you know, the more we automate these things, right, you don't have to be an automobile expert to drive a car, right? So you just, you know, my kids, I know they'll never look under the hood of the car, but they'll be able to drive. But maybe even they won't drive in, you know, 10 years from now. So I'm just saying that those are the kind of things that are a lot of wastage time. So a data scientist can be running hundreds of experiments, take on more projects, then focusing on one project for 4 to 8 weeks, trying to get the highest accuracy and overfitting, explaining and all of that. So all of that is getting automated in AutoML. So one last thing that I want to add here is that you can see the winning model is this, right? And the variable importance found by the winning model is here. You can't see it, but I can talk through this. This is for accuracy 1. When you go to accuracy 5 or 10, what happens is that multiple algorithms are competing against each other, trying out different things. And then the winning models across multiple algorithms, we build an ensemble on top of that. That's kind of like the Kaggle Grandmaster recipe. If you look at any Kaggle contest, they will always be combining like XGBoost and deep learning and TensorFlow and finally like a big ensemble. We build like multiple ensembles, and there is a big process there because, you know, it's collective wisdom from multiple models that's actually going into the ensemble to give you the really highest accuracy, like 10% or 5% lift with no overfitting. So that's like the ultimate thing. And if you think about all of the things that we found here, the next question is like, how am I going to move this to production? How does a production look like? So you can see a download Python scoring pipeline here. I didn't start with the Java, but you should also be able to download a Java jar file, standalone jar file that has all the feature engineering, all the transformation, pipeline, ensemble, everything built into the jar file. So you can take the jar file, give it to DevOps, and they can actually deploy it for batch scoring or real-time scoring. It's really as simple as that. So you start with the CSV file, you end up with a jar file or a Python scoring pipeline, and then you're going to be able to deploy it in production. And so we've done all of this. Now your business comes and says, great, now you're in production, tell me what's going on. And this is where the machine learning interpretability feature comes into play. So for the same, this use case, I've actually, so this is a standalone feature in the product. Either you can look at models that are built in driverless AI, even if it's a complete black box model with ensembles and XGBoosts and TensorFlow, we actually basically open up that box for you, okay, and show you what's inside a model. Now you can have a really good conversation with the business. So maybe I should just start with a simple, so here is the feature importance. Even though we created thousands of features, when we are actually explaining to the business, we only show you the columns that are the original columns. So everything that happened that you saw, like the clustering and the combination, doesn't make it here. This is a simple explanation of what your model contains. We actually reverse engineer the predictions, and then we build the machine learning interpretability out of it, and then try to infer what's going on. So, so the top one here tells you that these are the features. The first one is the number of employees. The second one is the Euro index. There's Euribor. There's an exogenous data that's actually driving customers to open term deposit, and it makes a lot of sense. If the interbanking borrowing rate is really high, the interest rates are high, then you would or would not open a term deposit. It's directly correlated to there's a reason why people buy CDs. Right, because they get fixed an interest rate and they feel like the interest rate is going to go down, so they want to lock into a really good interest rate. So this comes, the exogenous days, the data comes right on top. So now you can tell the business, this is exactly why people are doing what they're doing. And the second one is the number of days. The P days variable is really about how many days have gone by when the marketing campaign has actually reached the customer. It's like a lost contact point. The third one is the outcome, which means that the customer either clicked on an email or responded. The month seemed to come on top. So there's like a bunch of variables. So depending on your data, this could be like very extremely interesting. And you can actually get insight. Now, if you just look at the BI part, if you just directly went to the BI without AI, you may miss all these things. You'll see all those trends, but when you look at this and you look at the BI graph, it'll be like hindsight 2020. You just look at it and it just pops right back. Now you can interpret your BI reports. The whole point of AI is to build a model, break it up, and show you why it's accurate, right? And here's an interesting graph. This is called partial dependence plot. To me, this is like, so let me bring up the exogenous index, the Euribor index. You can see that the effect of Euribor index alone on the outcome, okay? So up to this values, there is a big bump in the term loan getting, the customer saying yes to the term loan. So there is a cutoff point here, after which, there is not much importance from the index. So the index is useful only up to a certain range. After that, it just washes out. So you want to find that. You want to be able to say, now you can tell, as soon as it reaches this point, now we can actually push the product, like CD products more, right? So you're getting a new insight from here. Similarly, you can look at drop down and look at different variables and see what's the conditional effect on that variable alone to the final outcome, right? All the variables play an important role in the final outcome, but each one of them have like a conditional effect, not a uniform effect, but certain values could actually drive the output more. So you can actually find those little things in the data. Now you can have a very intelligent conversation with the business saying that, this is what we should be doing, this is what we should be watching, talk to the marketing and say, when these things come, then we should probably launch a campaign or do things like that. The part of the reason why, again, AI adoption is black box, and we can see that we're bringing it a little bit more white box. And also, the dots here is from the test data set where we scored all the customers. And if for a particular customer, if you want an explanation, or if you have an agent talking to that customer, and let's say your AI basically said, yes, we're going to open a term deposit, then on the right side is a global model, but you really want to know for that particular customer what is important. So you can see that a consumer price index for that customer is has a big attribution to the output, followed by age and followed by the month. But the Euribor index is having negatively attributing towards it, just for that customer. So you have a global picture, and then after it's actionable, customer by customer, we can actually give you reason codes. The AI is actually giving you reason codes on why it is scoring the way it's scoring. And this is extremely important for regulators, right, to know why a loan is being denied, what are the different reasons, and you should be able to explain that as well. So that is part of the machine learning interpretability feature in this product. There's a lot more to it, but I just don't want to go too much. This documentation, you can download and play with this data. So Patrick signaling that, yeah, I think we're probably over time, but thank you all for coming. And yeah, thanks for being patient, going through all this stuff.